Welcome to part 3 of my logarithm video series. In this video we are going to solve equations, logarithmic equations and exponential equations. In order to do that we need to, you probably want to go back and watch part 1 and part 2 just to get a basic idea of what a logarithm is and especially the connection between logarithms and exponents. Right? And that relationship is going to come into play a lot as we solve equations today. And the first thing I want to do is take a look at these two cancellation laws. These are, more sort of ammunition that we are going to use to solve equations involving logs or exponents. So in the first cancellation law, sometimes these are called inverse laws or inverse properties. You might see an equation that has, a to the x equals something. Maybe that a is like an 8. Maybe it says like 8 to the x equals, 5 or something like that. If you see something like this, you want to try to get that exponent, that x out of the exponent. And to do that, you want to sort of undo the exponent. And the only way to do that really is to take the logarithm base a of a to the x. When you do that, these two things cancel out. Log base a of a cancel, leaving you with only the x. Alright, and that's how you would get rid of, a to the x. So if you had like 8 to the 5th equals, or rather 8 to the x equals 5, like I showed you a few seconds ago, what you would do is you would take log base 8 to both sides. And what that would do is, by taking log base 8, these cancel out, leaving you just with x equals, and then in your calculator you would just hit log base 8 of 5 and get your answer. The second one, when you have a problem like this, right, log base a of x, so maybe this is like log base 7 of x, what you want to do here is somehow get the x by itself, right? And to do that, all you need to do is sort of exponentiate the problem. So take this and raise it as an exponent with a base of a. So you're trying to match this with this. When you do that, these cancel out, leaving you with just the x. So in this example, log base 7 of x equals, let's say, 13 or something. You can use the relationship, which we'll talk about in a second, but you can also do this. 7 to the log base 7 of x equals 7 to the 13th power. So we're trying to match this number with this number, and the reason we do that is so they cancel. So x equals 7 to the 13th power. So those are your two cancellation laws, or your inverse properties. This one right here, you can probably solve a little easier using the relationship, which we'll go back to in a second. That was in part 1. That's like the big thing that we introduced in part 1, is this relationship in logarithms. There's also a one-to-one property that you want to familiarize yourself with. If you see log base a of x equals log base a of y, and your job is to find the value of this or something like that, all you need to do is understand that if they have the same log bases, then set the numbers equal to each other. For example, if you see log base 12 of x equals log base 12 of 7, then x equals 7. That's the one-to-one property. Alright, so there's 3 sort of tools that you can use to solve these equations today. And of course, don't forget the good old relationship. So if you have log base a of y equals x, it's a to the x equals y. So in other words, log base 8 of y equals 10. 8 to the 10th power is equal to y. Okay, so let's use those 4 things and solve a bunch of equations. Let's go pretty quickly here. Number 1. Here we have log base 4 of v equals 3. So there are two ways to solve this. You can use your relationship and just say 4 to the third power equals v, or you can exponentiate 4, raise this, and you do that. So now we use the one-to-one, where we have the same base. If the bases are the same, then the exponents are the same. Or that's not true. That is true, but I said that wrong. The reason I would do this is to cancel these out. So now I would get v equals 4 to the third. And you can see they're the same thing. Number 2. And whatever 4 to the third is, you would maybe go to your calculator. 4 times 4 times 4 is 64. Awesome. So v equals 64. Number 2. Here we have negative 10 log base 9 of this little binomial equals negative 20. Let's get the logarithmic expression by itself first. So I'm going to divide both sides by negative 10. That leaves me with log base 9 of p plus 6 equals positive 2. So here I can use my relationship. So I say 9 squared equals p plus 6. So that's 81 equals p plus 6. So that's 75 equals p. And I'm done. If I don't want to use my relationship, over here I can use my my second property above, where I can say, okay, 9 raised to log base 9 of p to the 6th equals 9 to the second power. The reason I would do this would be to cancel these out, leaving me with just p plus 6 equals 9 squared. And you get the same thing, 75. So pick your favorite method. Number 3. Here we're going to use our one-to-one. I can see that log base 12 and log base 12. So I'm going to simply set 14 equal to 3a minus 10. So I'm utilizing my one-to-one property. So 24 equals 3a. A is 8. Number 4. Here we're going to use our log properties, our division property from video part 2, where we say, okay, if I have the same base in each and I'm subtracting, that translates to division. And I know this has a base of 10. So if I use my relationship, it's 10 to the first power equals x over 9. 10 to the first power is 10. Multiply both sides by 9, you get x equals 90. If I didn't want to use my relationship, you can also do this. You can say, okay, I'm going to raise this whole thing up in my exponent. Same thing over here, 10 to the first power. The reason I would do that is to cancel these two things out, leaving me with x over 9 equals 10 to the first power, and I'd solve it. Number 5, same thing. Part 2 of my 3-part series has my properties. If I have addition and our bases are the same, I can condense those. Log 3 times 4x equals log 7. So we have the same bases on both sides. Base of 10, base of 10. So just set, this is 12x. Set 12x equal to 7. So x is 7 over 12. Number 6. Here we have natural logs, right? If you were so inclined, I'm not going to do this, but you can change all of these ln's to log base e. If you remember that ln is the same as log base e. The natural log is log with a base of e. I'm not going to do that though. I'm going to understand that these bases are the same and we're adding, so keep the base and multiply the arguments together. And the one-to-one property says if I have ln on left, ln on right, then this is equal to this. Distribute 3x minus 30. So 3x equals 86. And I divide 86 over 3. Moving on. Number 7. Again, all the same bases, which is good. So I'm going to keep that base. I'm subtracting. So log base 4. X plus 1 is my numerator. X is my denominator. Equals log base 4 of 54. Same base on both sides, so use my one-to-one property. X plus 1 over x equals 54. Multiply both sides by x. I get x plus 1 equals 54x. Get the x's on the same side. Subtract x from both sides. I get 1 equals 53x. So x equals 1 over 53. Moving on. Number 8. Same bases, so keep that base. We're subtracting up here, so I'm going to divide as I condense. That's equal to 1. So here I'm going to take one of two roots. I can use my inverse property, so I would say 5 raised to this whole thing equals 5 raised to this. As I solve that one, I'm canceling these out, leaving me with just that is equal to 5. So x squared plus 6 rather equals 15. I'll multiply that 3 over here. So x squared equals 9. So x is equal to positive or negative 3. Now you want to be careful with sometimes you're going to have extraneous solutions. You know, if you check both of these back in there, you might find out, I'm not going to do this because I still have a bunch of examples to get to, but sometimes you're going to find out that the answer is going to yield something that's outside of the domain of the log or the natural log, so just be careful. If one of them yields an extraneous solution, just kind of get rid of it. If you didn't want to use this cancellation law, you can just use the good old-fashioned relationship 5 to the first power equals x squared plus 6 over 3. So 15 equals x squared plus 6, and solve from there. Number 9. Alright, so here we finally we're getting into our exponential equations. So right now we don't see anything to do with logarithms. All we see is our variable that we're asked to solve for is in our numerator, or excuse me, in our exponent. So we want to get it out of there. And the only way to get it out of there is to use our first cancellation property that I just showed you above. So I'm going to take the log base 15 of 15 to the a is equal to log base 15 of 18. The reason I would take log base 15 is because those cancel, leaving me with a equals log base 15 of 18. And I just need to go to my calculator to actually get this value. So let's go ahead and figure out log base 15 of 18. So I type it in log base 15 of 18. The syntax has me put 18 first and then 15 after a comma and press enter. So my answer is 1.067. So let's see if that makes sense. A equals 1.067. So check it back up in here. 15 to the 1.067 power equals 18. That makes some sense to me because I know that 15 to the first power is equal to 15. So anything that's slightly above 1 should give me a number slightly above 15. Makes sense? Number 10. Here we have an exponential equation. Let's isolate this first. So let's divide by 6. Divide by 6. So I get 10 to the 3x power equals 47 over 6. This is what we're trying to solve for, the x that's in the exponent, so we need to get rid of that. Let's take log base 10 of both sides. Let me do it down here. Log base 10, I don't actually need to write the base because it's understood to be 10. So we'll take the logarithm of both sides. log base 10 of 10 cancels, and we're just left with 3x equals the right-hand side. So x equals log 47 over 6 all over 3. So let's type that into our calculators here. It was, let me move this a little bit here, log 47 over 6, close parenthesis, divided by 3. 0.298. 0.298 is our answer. Moving on, number 11. If you want to try some of these on your own, this would be a good time. In this one we have an n in our exponent, so we want to get rid of that. First thing I'm going to do though is isolate this whole exponential expression, get that purple thing by itself. So first thing we're going to do is add 7 to both sides. So if I add 7 to both sides, I get 83. Now I'm going to divide everything by 6. So I get e to the 9.3n plus 9 equals 83 over 6. Once you have that thing isolated, once that's by itself, now all we need to do is get that variable out of the exponent. To do that, you have to take the appropriate logarithm of both sides, and the appropriate logarithm is going to be log base of this number. Log base e is actually ln, as you know. So let's take the natural log of both sides. The natural log of both sides will cancel these two, leaving you with just the exponent. And now all we need to do is just subtract 9. So 9.3n equals the natural log of 83 over 6 minus 9, and then divide the whole thing by 9.3. Alright, it's calculator time. I'll take this thing over here and go to my calculator. So I have the natural log of 83 over 6, close parenthesis, minus 9, enter, divided by 9.3. I get negative 0.685. Negative 0.685. And I'm done. Alright, this one is, you can do it a couple different ways, but I'm going to show you, I'll show you the way that we've been doing it so far first, and then I'll show you a different way. So here we have our x in our exponent. I want to get that out of there, so let's take log base 2 of both sides. Log base 2 of both sides. So these cancel, leaving me with negative 3x equals log base 2 of 64. So log base 2 of 64 over negative 3 is my answer. Calculator. Log base 2 of 64 divided by negative 3. I get negative 2. It's a nice neat number. Let's see how that works a little bit differently. So if I ever see a exponential equation that has this and this that can sort of be transformed into the same base. In other words, let's change 64 into 2 to the something. So 2 to the something is equal to 64. What I'm trying to do is just match these bases up. So let's see, I know that 2 squared is 4, 2 to the third is 8. So 2 to the fourth has to be 8 times 2 is 16, 2 to the fifth is 32, 2 to the sixth is 64. So 2 to the sixth is 64. All I'm doing there is just transforming 64 into 2 to the something. So I get 2 to the negative 3x equals 2 to the sixth. The reason I did that is so now I have these two bases. When those two bases are the same, just set their exponents equal to each other. Negative 3x equals 6. X equals negative 2, which is what we got earlier. So it's kind of a cool trick if you can sort of base match. 13. I guess I skipped 13. 14. Here we already have the same bases, which is nice. If the bases are the same, just set your exponents equal to each other. So let's gather these v's on the same side. 2v plus 2v equals 0. So 4v equals 0, v equals 0. That makes sense, right? If you plug that back in and you checked it, if v is 0, then 2 times v is 0. Negative 2 times v is 0. So 1 equals 1. That checks out. All right, and I suppose if you didn't see that one-to-one property, you could take the long route. You can say, okay, I've got my v's in my exponents, so I want to get those out of there. So let's take log base 5 of both sides. Log base 5 of both sides. What that's going to do is take these and cancel them, leaving you with 2v equals negative 2v, and you'd solve it. So I guess my point here is that, if you know your shortcut, go this route. If you don't, you can still get the right answer. It's just going to take you a few more steps. So the more tricks you know, the easier these problems will be. Last one. I've got 5 to the p minus 2 is equal to 625. Give this a shot. You can solve this a couple different ways. What I'll do is I'll say, okay, I know that 625 is 5 to the something. So let's see, 5 squared is 25. 5 to the third power is 25 times 5, which is 125. 5 to the fourth power is 125 times 5, so that's 500 plus another 125, so that's 625. So 5 to the fourth power is 625. I just matched those bases up. So now p minus 2 is equal to 4. P is equal to 6. And if you didn't see it that way, that's okay. You can take log base 5 to both sides. Log base 5. So these cancel out. P minus 2 is equal to log base 5 of 625. And remember this, log base 5 of 625, if I'm looking to actually solve that, you would say, okay, 5 to the what power equals 625 using my log relationship. 5 to the x power equals 625, and that answer, of course, is 4. 5 to the fourth power is 625. So you're doing the same thing. So this would be p minus 2 equals 4, and p is 6. So there you go. There are 15 examples, about a 23.5-minute video or so, on solving equations, logarithmic and exponential equations. There are a lot more examples I can do, and I might make a sort of separate video in the future that addresses maybe more complicated exponential and logarithmic equations. But for the most part, if you can get these two cancellation laws down, the one-to-one property, and continue to remember our good old relationship, you're going to find some success. So thanks for watching, and I'll see you in the next video.